So now let's just switch back to the slides and just go through the treatment of the residual network from the slides, right? So it's exactly repeating what we were talking about, right? So in the original edge, like look at any original edge as part of the input graph, right? So now there are two pieces of information. The first piece of information would be the capacity of the edge, right? That's already given in from the very beginning as part of the input, right? The second piece of information is at this moment what our flow looks like, right? So how much capacity we have used when we look at our current solution, right? So if you look at this particular instance, let's just imagine that there's an edge that's moving from U to V, and its capacity is 617, and we are already pushing 6 unit of flow from U to V, right? That basically means that we sort of need to introduce and reverse edge to highlight the fact or represent the fact that we are able to undo those flow that were already sent, right? So in the residual network, what we need to do is to introduce a so-called reverse edge. The edge is really just pointing from V to U, right? And the capacity of the reverse edge will really just be the flow value, right? So this is really used to represent the fact that we can regret for 6 unit, right? So for we can sort of undo 1 unit of flow from U to V, or 2 unit, and so on and so forth. We can undo up to 6 unit, right? So this is how we define the residual capacity, right? So for any of the edges, in case it's original edge, that would be straightforward, would be the capacity minus what we have used so far. In case it's a reverse edge, then we would be really just use the what we have used, the flow information what we have used so far, right? So this corresponds to 6 here, right? So this is actually the one of the less subtle case. Let's also discuss about one of the more subtle cases, right? So let's imagine that we have in our original graph, it looks like that. I'm able to send 20 unit of flow from U to V, and I'm also able to send 10 unit of flow from V to U, right? So basically you really just imagine that there are two pipelines, right? Two pipelines, like one pipeline that is moving from one direction from U to V, the other pipeline is moving from the other direction, right? So basically if you look at the water pipeline, you can really just imagine that physically it's two, right? It's not it's we cannot really just consolidate this two piece of information, right? So and let's just assume that at this moment we already used the 5 unit of flow moving from U to V. Now we sort of want to construct the residual graph, right? Let's see how we can construct the residual graph. And let's draw an U and V again, right? So basically, let's first examine how much flow I can push from U to V, right? Because I already used the 5 unit of flow, right? So I can only push 15 additional unit from U to V, right? So now the second thing is that I want to decide the amount of flow I can send back from V to U, right? The first thing we know that is we never touch the pipeline that's moving from V to U, right? So basically the 10 can be copied here. But on the other hand, we sort of like want to reflect the fact that we do want to be able to regret or undo our decision, right? So by our definition, we really want to add and reverse edge that's connecting from V to U, right? So there's 5 unit of flow, right? So now that comes a bit a bit of interesting thing, right? So you can sort of physically imagine there are two pipelines that are moving from V to U. The first pipeline would be the original one, right? That's already we already seen from part of input. The second pipeline is really just that the fact that we can do that, we can regret and then just send back 5 more unit of flow from V to U, because I sent 5 unit of flow from U to V at this moment, right? So now it's sort of this graph, it's sort of an edge, right? There are two edges that are connecting from V to U, right? So you really just imagine that there are just two pipelines. There's nothing strange going on here, right? But what we can do is really to simplify a little bit, right? To consolidate this two number and come up with a final residual graph that looks like that, right? So it's 15 units going this direction and another 15 unit going to the other direction. So in our example, right, these two although both are 15, but it comes from two different calculations. The first 15 comes from 20 minus 5, right? 20 minus 5. The second 15 comes from 10 plus 5, right? So despite that these are two numbers, right? The two numbers that the same numbers appear twice, they calculate from very different ways, right? So that basically physically just means that so at this moment I'm both able to push for 15 unit of flow from U to V and also push up 15 unit of flow from V to U, right? Let's just imagine what happens. What happens if I really want to push 15 unit of flow from V to U, right? That basically means that what we can do is that first revert back this decision moving from 5 to 0, right? So 5 unit really comes from the revert or undo the decision, right? This is the 5 unit. On top of that, I can continue to utilize the 10 unit of capacities of the pipeline that's connecting from V to U, right? So this is 10, right? So at the end, after I do both things, I will come up with a graph, right? The new flow graph will looks like that, U and V, and there are only 10 unit of flow moving here. There's no flow moving there, right? So these are the new flow graph. Right. So this example just shows that, right, indeed it's possible to push a total number of 15 units of flow on top of the existing solution. What we will get, you will just get a flow that's moving from V to U, that's 10 units, and then there's no flow that's moving from the other direction. Right, so basically, this is actually represents one of the more subtle cases where like there are two pipelines connecting both U and V and U, right? But otherwise, the whole thing is really quite straightforward. You come up with an edge. You keep two pieces of information. One will be the flow information. The other one will be the capacity information, right? So and then you keep two edges. The original edge you just use the capacity minus flow. And the second edge, you just copy the flow, right? This is exactly how we define the residual capacity, right? So in case it's residual, it's a reverse, then use the flow information. In case it's not reverse, use the delta between the capacity and the flow, right? So, but in case like there are two directions, in the original graph, there are already two edges, then you need to be a bit more careful in sort of using this definition. This definition is not wrong. It's really just that it doesn't help us to consolidate. And it doesn't guarantee that this is a simple graph in the sense that there could be multiple edges that are connecting two nodes. Right. So let's really just articulate what is our residual network, right? So as we mentioned just now, it consists of two types of edges. The first would be the original edge that doesn't hit the capacity limit yet, and the second type would be what we call the residual edge, right? So that would be the set of the edges in the residual graph. And then let's also talk about the key properties here, right? So there's an if and only if property here, right? That really just means that if I look at the residual graph, right? So let me just erase that a little bit. If I look at the residual graph G of t, if there exists xt pass in the residual graph, or more specifically, if there exists an f prime flow that we can push through in the residual graph, that really means that this new additional flow can be integrated into the existing one, right? So the f is the existing one, right? And similarly, right, this is an if and only if direction, so that means that it's both directions are right, right? So similarly, for any flow f prime that's such that after we add this new flow in the existing one, this is still part of feasible flow. It's a feasible flow. That also means that the f prime will also be a feasible flow on its own in the residual graph, right? So this is a if and only if the directions, right? So basically that means that if we found an optimum solution if and only if in the residual graph and ST are disconnected from each other, right? So this is very high level idea of the residual graph, right? So now we can talk about the augmenting path, right? Augmenting path is really just a simple path that's in the residual graph, right? So that's really just like what we have been doing, right? So every round we found a residual graph, we try to find an ST path, right, in the residual graph, right? That's like in mathematical terms, that's what we call the augmenting path, right? And then there's a bottleneck capacity. Basically, it's really just that in one of the augmenting paths that's connecting from S to T, right? It's this 5, 3, 2, right? So we sort of need to know that how much additional flow we can push through on top of this graph, right? This is really just that I take the mean of all these three numbers, right? So so when they write down this whole idea, it's really just what's written here, right? So it's an augmenting path, and then if I look at the residual capacity of all the edges on this path, I pick out the minimum one, that will be the bottleneck capacity, right? So now if I look at this this algorithm, right? It's really just that once I found the augmenting path, I just determine the bottleneck, and then I update. I do the update basically is that so again, like if I draw this residual, the augmenting path again, 532. If the bottleneck would, in this definition, would be the 2 bottleneck. Bottleneck would be 2, right? So that basically means that I want to be able to push 2 units of flow, right, along the whole path, right? So after I push the whole 2 units of flow, what I need to do is that I need to do two things, right? So the first thing is that I need to sort of update my flow, my flow. So this I need to sort of update the flow, right? Fe is the flow, right? So we also need to reverse, keep track of the information related to the reverse edge, right? So basically the whole thing is actually what we have done just now, the example we have done just now, right? Every time we update a path, we sort of also want to update the residual network, right? This is the whole highlight. So this pseudocode over here just reflect what we have done just now. Basically, it's really just that we start with the residual graph. We find the ST connected path and update the residual graph, and I keep doing that until that even within the residual graph, S and T are not connected anymore, right? So basically, it's really just that pseudocode or summary of what we have done just now, like the example we have seen just now. So now let's move to the more important part. The most important part of this chapter is really just the maximum mean cut theorem, right? So I think today we just have time to talk about the flow value lemma, right? So let's talk about what does this lemma say, right? So let's consider an arbitrary flow, right? This would be the flow we have constructed so far, and let A and B be an cut, right? So the cut really means that S belongs to A and B belongs and T belongs to B, right? So it's cut, right? So it's both a partition, and on top of partition we need to enforce that the source is one set and the destination in the other set, right? So with the flow value lemma basically says that there's a way for us to compute the total flow, right? So if I just look at if I look at this partition, right? So let's imagine the partition looks like that. This is our A, and this is our B, right? And then there's a way that allows us to compute the flow level, the total flow of this solution, right? So the most obvious way to compute the flow is really just I sum up all the numbers that are coming out of S, right? So this is 10 plus 5 plus 10, right? So this is 25, right? But then I can also, right, use this partition to sort of to help us to understand the total flow forward. The amount of flow we are sending, like using this F solution, right? So basically that means that if I count, like imagine that these are just the two islands, I count all the waters that's coming out of the island A, and minus all the water that's really coming back to the island A, then the delta here is exactly the water that's sending from S to T, right? So this is actually a very intuitive lemma, right? So just imagine that like what we did last time, right? There's a very powerful adversary that cuts the pipeline, the whole network into two islands. The first island contains S, the other island contains T, right? So there are quite a number of bridges, right? From moving from S to T, and there are some bridges from moving from T to S. Right. So now I sort of want to use the flow that circulates across the bridges to help us to understand the total amount of water that's sending from S to T, right? So let me just repeat what I'm saying here, right? So I want to come up with a way to measure the total amount of water that's sent from S to T. What we really need to do is really to examine all the bridges over here, right? All these bridges, right? I just count. I look at every single bridge and count the amount of flow that's moving from the left side of the bridge to the right side of the bridge, and count the amount of water that's moving from the right side of bridge and to the left side of bridge, right? I take the difference. That would be the total number of water that's moving from S to T. But from the island left to the island right, right? This is island left, this is island right, right? So if I just count the bridge information, then I'm able to see the total amount of water that's moving from left to right, right? But the only possibility, right? So if I have 1 unit of water that's moving from left to right, eventually that really just means that, like, the only reason there are water that's moving from left to right is really just that there are some water that's pushed from S to T, right? So if I see 1 unit in total, that means that there's 1 unit of flow that's moving from S to T. And we can sort of generalize these arguments to really come up with a way to calculate the value of the flow. It's really just that we look at all the water that's coming out of A minus all the water that's coming back to A, right? So let's use this particular example, right? So the island A consists of everything except the last load, right? Now in this case, the total amount of water that's coming out of that's coming out of the set A is really just the 5 unit over here, 10 unit over here, and 10 unit of here, right? There are no water that's moving from to the reverse direction. So I sum up all these 3 numbers is 25, right? So now let's also look at a second case, right? So in case my partition looks like that, this is A and this is B, right? So again, if I count all the waters that are moving out of from S to B, right? So it's really just summing up all these 3 numbers. Again, I get a number that's 10 plus 5 plus 10, right? That's again 25, right? That's again what we need, right? So next, like this is a third example. So the slide's giving us 3 examples to do the partition, right? So 3 examples. So all this example really just says that regardless what sort of partition it is, so long as it's a cut, this flow lemma always holds, right? So the first cut looks like that, like A and B, cut that into one larger island and one smaller island. The second cut is to make A as a small island, make B as a larger island, and still works, right? The number still matches up, right? The third case is really just making things a bit more subtle, right? So we sort of make A to be the set of black nodes, right? So A is the all black nodes, right? And B are the all white nodes, right? White nodes, right? So now here we want to be a bit more careful in calculating both terms, right? So I want to compute the set of edges that are coming out of A, right? So these are actually the black edges, right? The black edges are the edges that are coming out of A, right? So if I look at all the black edges, it will be 10 plus 10 plus 5, right? Plus 10, another 10, where is the another 10? Another 10 is over here, right? So, and then there are 2 zeros. I'm not using any flow here, not using any flow here, right? So those are this correspond to the black edges, right? Black edges, right? So it's bit pay attention. We use black edges and black nodes, right? A consists of a set of all black nodes, right? So, and now if I look at the blue edges, right? This looks blue, right? So 5, 5, 0, 0, right? 5, 5, 0, 0 all the blue edges are really moving from B to A, right? That corresponds to this term, the second term, right? 5, 5, 0, 0 is what we get at the end, right? So we need to do the subtraction, take the difference. After I take the difference, I tediously calculate everything. I come up with 25 again, right? So that really the whole moral of the story here is that regardless what sort of cut you come up with, like even if with this very funny way of doing the cut, right, eventually we are able to come up with to calculate the value of the flow. Value of the flow basically means that the total amount of flow we are pushing from A to B, right? So now we sort of want to give a proof for this lemma, right? Just now we sort of used the island example to sort of give you some sort of intuitions, right? So now we sort of want to make this rigorous, right? So now the first line, right, value of the flow equal to E out of S minus E into S, right? This is the straightforward, right? We talk about We talk about that in our previous lecture, right? So the value of flow, I just look at the source node, calculate all the total amount of flow that's coming out of source and the total amount of flow that's coming back to S, right? So in the optimal solution, there shouldn't be anything that's coming back to S, but in order to define this value of the flow rigorously, we still need to consider this case, right? So now the second thing we want to do is really just that so we sort of want to say imagine that I have a graph, right? So this is the A, this is the B, right? This is the S. Let's assume that on top of S I also have V1, V2, V3, right? Let's just say there are only three edges that have three nodes that are within S, right? And this is T, right? And there are a lot of other edges that we don't need to care about, right? So moving from here to here is basically says that I can have E out of S, Fe minus E in S, Fe, right? I can add a lot of dummy useless terms, right? I can also add E out of V1, Fe1, E, and then minus E inside V1 Fe, right? I can add these terms, right? So I can sort of look at all the value that's coming on into V1 and then all the value that's going out of V1, right? So this term is actually 0, right? If I add a 0 term, it will make things unchanged, right? So that's the reason I can feel free to add this term, right? I can similarly add the second term, like E out of V2 Fe minus E inside V2 Fe, right? So I'm really adding a lot of dummy terms, right? So this is also 0. This term equal to this term over here. And now I can add a lot of dummy terms, right? So in general, I can add all the V's inside 8 to this equation, because I'm just adding a lot equal to this little term plus a lot of zeros, right? Adding zeros doesn't change the solution, right? The reason this is 0, right? It's really just the flow conservation condition, right? Conservation condition is you look at any node that's not neither S nor T, then the amount of flow that's going in has to be the same as the amount of flow that's going out, right? So that's the reason that the second inequality holds, right? So let's just erase everything and let me just repeat the argument over here, right? So from here, from the second line to the third line is really just that I'm adding. So instead of just really looking into S, I look into all the nodes inside A. But when I look at all the nodes inside A, what I'm effectively doing is really just add a lot of zeros, right? So by flow conservation constraint, all terms except for S, V equal to S, they are all zero. So that's the reason the equality holds here. Right. Finally, let's also look at the equality in the third one, right? So the equality in the third one sort of says that, well, I don't really need to look into the internal edges, right? So you can sort of see that what the English is written here is that V out of A, E out of V, right? So these two English terms collapse into E out of A. So let's also just draw what's going on here, right? So let's even make one more simplifying assumption. Let's say that there are only two nodes right here, right? So now let's say what we are doing here, right? So now if you can calculate the V, so basically now if you calculate V out of A, right? So what are the V out of A and E out of V, right? If I just look at these two terms, right? Let me just write this out, right? So I want to look at all the edges, E out of V and V out of A. V inside A, right? Sorry. V inside A, right? So let me just repeat what I'm doing here, right? So I want to count all the edges here, right? All the edges here, if I just put these two terms together, it's really E out of V and V inside A, right? So let's count all the edges that has this property, right? So A consists of S, V1 and V2, right? So and let's just do things one by one, right? So if I look at the S, and I want E out of S, right? So basically the edges are these two, right? And if I also count the V1 this would be the edge here. And I count V2, this will be the edge here, right? So these are all the things I'm summing up, right? These are all the 4 edges I'm summing up, right? So now if I look at the if I look at the V out of A and the E inside V, right? So let me just draw everything again here, right? So we want E inside gets into V, V belong to A, right? So if I look at this term, right? So there are 2 summations going on here, right? Let me just erase this part, right? Erase everything. Let me just do the expansion a bit more careful, right? So this term is actually the same as V out of A, V inside A, and E out of V, and FE minus V inside A, coming into V, FE, right? So I'm just using the associative rule to put all the summation together, right? So for the first part of summation, those are correspond to the green edges, right? Right. For the second part of summation, I'm also trying to draw things a little bit out, right? So again, A consists of this three component, and if I look at S, there are nothing coming into S, right? So I don't need to calculate anything. If I look at V1, that's the edge that's coming into V1. This is the edge that's coming into the V1, right? So into V2, right? So when I do the subtraction, it really means that I want to use the green edges minus blue edges, right? So now if I look at this green edge, the green edge from A to V, S to V1, and then blue edge from S to V1, right? So the first part, this 2, if I use the green over here minus the blue over here, this is 0, right? Similarly, if it's moving from S to V2, right? So it's counted in the green edges once and counted in the blue edges once, right? It's also 0, right? The only thing that we cannot subtract is really those things that are really going out of A, right? So those are when I have a cross edges. When I have a cross edges that are not subtractable, right? So for the rest of them, the edges are all cancelled, right? So this explains the first term, right? So there are also cross edges. It also could possibly be that there are cross edges that's coming inside A, right? So this is the second term, right? So that's sort of a high level reason that moving from the second first to second inequality, from the second inequality to third inequality, is really just the internally the edges cancels each other cancels, right? After we remove all the edges that cancels each other, the only remaining terms would really just be the edges that's coming out of A, and those edges that are coming into A, right? So basically, it really just becomes that I need to count all the edges moving from A to B, minus all the edges that's moving from B to A, right? These are really just the intuition here. So for any edges that are within A, right, it will be counted once, right? It will be counted once in this term, or this term here. Right. It also be counted once in this term, and maybe it's also this term here, right? And then when we cancel, and then this will be counted twice, right? But it cancels out each other, right? It plays no role, like it has no impact on the entire sum, right? The only impact we see is really just the cross edges, either moving from A to B or moving from B to A. Right. That's the reason we have this the flow value lemma, right? So if I look at any cut, I just look at what's going on within the cut, then I'm able to calculate the value of the flow, right? So this is again the very high level intuition is that you count the water that are circulating across the bridges, right? So eventually, if you found that there are 5 units of water that's moving from the left island to the right island, there must be the flow that's coming out of S, right? All the flow that's coming out of S will eventually move across the island, and that's the reason that if I just count what's going on on the bridges, then I'm able to calculate the value of the flow, right? That's the high level idea, right? So I think we are running out of time. So from the weak duality to the strong duality, we are going to cover that in the next lecture. Thank you.